Welcome to the lecture number 18, speed control of induction motor. In the previous lecture, we have seen equivalent circuit of induction motor. We have seen the flow of power right from the stator to the rotor and shaft. We have also seen the principle of operation of induction motor in earlier classes. So, the objectives of today's class are to understand the parameters governing the speed of an induction motor, then to study the methods for speed control of induction motor and gain the knowledge of application of speed control of induction motor for industrial use. Actually, the slip of an induction motor varies in a narrow band from no load to full load. When the motor is running at no load, speed is very close to the synchronous speed, and based on the torque requirement, load requirement, the speed falls in a very narrow band. So, the induction motors are suitable for most of the industrial application which do not require any speed control. For example, say lathe machine, we are having other industrial applications like irrigation pump operation. Once the pump is started, whole night the irrigation is going on and there is no need to speed control. However, few techniques are available to control the speed of induction motor. Still, the induction motor drives is inferior to DC motor drive. In case of DC motor drive, the smooth control of speed over wide range is easily possible. For example, in steel tubes industries, where we have to draw the pipes, then speed control is it is carried out with the help of DC machines. In many industrial application where wide range is required, we still prefer DC drives. In case of traction, we are using DC series motor. So, for such purposes, this type of induction motor, they are not suitable. Today, we will discuss the speed control of induction motor, but still the speed we will get after controlling is say somewhat in steps. One cooler fan is there at your home. You can run that cooler in slow speed, medium speed and high speed. So, basically we are able to change the speed, but it is not very smooth speed control over the wide range. The synchronous speed of resultant rotating magnetic field, it is given by 120 ns synchronous speed, it is equal to 120 f upon p, where f is the frequency of the supply, p is the number of poles of the motor. So, when we are feeding the power to the stator of induction motor, the rotating magnetic field starts rotating at synchronous speed. Synchronous speed minus rotor speed divided by synchronous speed, this is known as slip. S is equal to ns minus nr upon ns. So, SNS is equal to ns minus nr, and hence the nr, the rotor speed, it is equal to ns minus sns. So, it comes as 1 minus s into 120 f upon p. This is the rotor speed. So, just see the equation. Rotor speed is function of f, p and s. From equation 1, it is clear that number of poles of the winding and the frequency of the supply determines the synchronous speed of resultant rotating magnetic field. The rotor tries to catch the synchronous speed of this rotating magnetic field. Now, if somehow this synchronous speed can be altered, then the motor speed will change accordingly. The rotor has to follow the synchronous speed. So, if we want to change the rotor speed, what we have to do? We have to somehow alter the synchronous speed. Now, there is another point. We note that torque produced by induction motor, it is directly proportional to square of the applied voltage to the stator. So, the variation of stator supply voltage, it can also be used for speed control of induction motor. The voltage control method is simple and economical way to control the speed of induction motor by adjusting the voltage supplied to it. Understanding the effect of rotor resistance on slip torque characteristics of induction motor, rotor resistance control may also be used for change of speed. However, this is applicable to only slip ring induction motor. In case of cage type motor, we are having no provision of insertion of any resistance. Thus, we can summarize the speed control of induction motor can be achieved from stator side by changing the number of poles of the stator winding. Second, by changing the frequency of the applied voltage. And third one, by changing the stator voltage. So, these three control methods, they are possible from stator side. Now, if we consider the control from rotor side, so changing rotor circuit resistance, of course, this is it is not applicable for cage type motor, it is valid for slip ring induction motor only. And then from rotor side, another method is there, secondary foreign voltage control. Now, apart from these two methods, there is one more scheme, cascaded operation. By cascading two induction motors, we can also achieve the speed control. So, one by one, we will study various types of speed control, and first one in this category is speed control by changing the number of poles. This method is mainly applicable to a squirrel cage motor. Why? Just think. Yes, the beauty of cage type motor, we know the cage winding automatically adopts the same number of poles as that of stator. So, this method is not suitable for wound motor due to complications involved in simultaneous switching in both stator and rotor winding to change the number of poles. The number of poles pair in stator can be changed as follows. Number one, by providing multiple stator windings. In this method, two or more independent windings are placed in the stator slots. Each winding is designed for different number of poles, and the supply is connected to any one of the winding at a time. If the winding having 4-pole configuration is energized with 50 Hz supply, it will produce rotating magnetic field of 1500 RPM, 1500 RPM synchronous speed. Now, suppose if the supply is disconnected and next time it is applied to another set which is wound for say 6 poles. Suppose this time the synchronous speed of rotating field will be 1000 RPM. Ns is equal to 120 F upon P. What we are doing? We are altering the number of poles and accordingly Ns is changing. The rotor speed will vary accordingly. The stator may be designed for 2, 3 or 4 sets of such independent windings, and with the help of selector switch, provision of slow, medium and high speed, it can be obtained by connecting any particular set at a time. So, to summarize this particular method, we are having simply cage type rotor. On the stator, we are having different sets of winding, say for 4 pole, 6 pole, 8 pole. We are connecting supply to any one particular winding, and depending on the number of poles of that particular winding, corresponding Ns will be produced and the final speed of the rotor will set accordingly. So, what is the summary? We are not getting continuous change in speed. We are getting stepped response. Second technique of pole changing is by using consequent pole technique. In this method, number of poles can be altered by placing one or two independent winding on the stator and changing the number of poles by changing the interconnection of primary coils. Let us assume 6 coils as shown in figure, where a phase winding consisting of 6 coils, we are having 6 coils on the, they are clearly visible on the figure. Coil number 1, 2, 3, 4, 5 and 6, and they are divided into 2 groups. In first group, we are having coils 1, 3 and 5, they are connected in series, and the end points of these series connection, they are marked as A and B. In second group, we are having coils 2, 4 and 6. They are also connected in series with the end terminals C and D. Now, coils of these groups can be connected either in series or in parallel. Figure 1B and C, it is shown respectively. So, with this connection, the stator winding will create 6 poles. In the figure, it is very clear. Current is entering from terminal A. In coil number 1, it is creating south pole. Then coil 1 is connected to coil number 3. After third coil, current is entering to coil number 5. So, we can see that 1, 3 and 5, they are connected in series. So, current is entering from A and finally it is leaving from B. So, the poles created here in 1, 3 and 5, they are marked as S. Just feel the polarity of these windings. If you grip a conductor in such a way that thumb is indicating direction of flow of current, fingers will indicate direction of flux. So, you can visualize on the left hand side of the conductor, the direction flux can be imagined. Again, on the second conductor of coil B, marked downward. So, if you grip the conductor, the direction of flux can be seen. So, you can imagine that finally inside this coil 1, S pole is being created, and since 1, 3 and 5 they are similar. So, S pole is being created here. Now, in second set we are having coil number 2, 4 and 6. Remember, this time current is entering from D, not from C. So, from D it is coming to coil number 6, right side of the coil 6. So, here the direction is upward, then it is coming downward, then same is connected to coil number 4 and 2. So, set of 2, 4 and 6, it is creating north pole. And finally, in the screen you may see that we are having 6 poles. So, this is the connection diagram for 6 poles. Direction of current in first set, it is from A to B. Direction of flow of current in second set from D to C. The series and parallel connection, it is given here. So, in series connection, just see B and D point are short circuited. So, finally, out of 4 connections, 4 terminals A, B, C, D, what we have done? We have connected B and D. Now, current is entering from A, passing through coil number 1, 3 and 5, then entering from D. So, 6, 4 and 2, and finally from point C it is coming out. This is the series connection. Now these 3 sets can be connected in parallel also. In this case, one is connected to D. Now we are having 2 parallel paths. So 2 schematic diagrams are shown for series connection and parallel connection. Now everything is same. We are having 6 coils, but this time what game we are playing? Just see the diagram. The direction of flow of current in these 6 coils is such that this time we are creating 12 poles. Just observe the flow of current between the coils 1, 3, 4, 5, 6, we are getting north pole, and in between these as south pole is created. So this is connection for 12 poles. Those same set is producing 6 pole and 12 poles. Again the stator pole for 12 poles series and parallel connections are given, shown in the figure. If the direction of flow of current through the coil of group AB is reversed as shown in figure 2A, then all the coils of this set will produce north poles. Fluxes which are coming out of these north pole will now find path through the interpole space for going out. Hence south pole will be formed in the interpole space, and the stator will experience presence of 12 poles. The required direction of current through coils can be obtained by connecting 2 sections AB and CD either in series or in parallel as shown in figure 2B and C. Thus, each phase of machine winding has 2 coil groups, AB group first one, CD group second one, and which can be connected either in series or in parallel for both 6 pole configuration and 12 pole configuration. Now third method of speed control, it is by changing frequency of applied voltage. Again this scheme comes under control from stator side. So this method of controlling the speed of 3-phase induction motor allows for broad range of speed control with smooth transitions between them. However, the main challenge lies in providing a variable frequency supply. The necessary auxiliary equipment for this purpose lead to high initial costs, increased maintenance, and of course reduced overall efficiency. And consequently, this method is not commonly used for general speed control applications. But despite of its complexity, this method is highly advantageous in specific situations where its extensive smoothly variable speed range and effective speed regulation are particularly valuable. Have you ever visited any temple situated on the top of the hill and you have used the ropeway? In ropeway, on the very strong steel wire rope, trolleys are there and passengers are sitting on, and traveling. Now for operation of these ropeway trolleys, we are using slip ring induction motors. If you are, as students of electrical engineering, if you are going to visit such temples, I will suggest that you must visit the control room of that ropeway system, and you will find one panel is there. When the trolley system, ropeway system is about to start, in control room you will observe frequency is changing continuously, 5 hertz, 10 hertz, 15 hertz, 20 hertz, and slowly here the ropeway is picking the speed. Once the trolley is started, now throughout the span, the frequency is constant, 50 hertz. Now again at the time of stopping, the trolley has to stop at one particular point. One attendant may be standing there with lock and key to open the lock of the trolley gate, and the trolley stops exactly at the same place where it has to be stopped. So during this stopping action, you will find that again in the panel frequency is 50 hertz, 45 hertz, 40 hertz, 30 hertz. So speed is changing accordingly. So what type of control is this? We are controlling the speed. We are controlling the speed through frequency control. The third method of a speed control is speed control by changing stator voltage. This speed control method uses a constant frequency with a variable supply voltage. It involves adjusting the voltage applied to the stator to change the speed of an induction motor. This approach is straightforward, inexpensive initially, and has low maintenance cost. However, it is limited in its application due to several factors. Operating at voltages higher than the rated voltage, it is constrained by magnetic saturation. A significant voltage change is needed for only a small change in speed, and the torque produced, it decreases significantly with reduced supply voltage, and the motor may stop if the load torque exceeds the motor's pull out torque at lower voltages. And this method offers only a narrow range of speed control, particularly in reducing speeds from the rated speed. The effect of change in voltage on speed torque characteristics or slip torque characteristics, it is shown in figure. It is obvious that with the reduction in applied voltage for load having load curve like fan, the speed drops to an extent. In the figure, you may see the characteristics of fan load, and for 3 voltages V1, V2 and V3, where V1 is greater than V2, V2 is greater than V3. So if higher voltage is given, we are getting high starting torque, and we know that the rotor speed will adjust in the stable region of this slip torque characteristics, and the point of intersection will decide the speed. So with V1 as the voltage and the load curve, it is cutting at one particular point, and accordingly the rotor speed is say N1. If the voltage is reduced, now the motor will start running at speed N2 with applied voltage V3. N3 is the speed of the rotor. So by changing the voltage, we can obtain speed control of induction motor. So typically this method of speed control by changing the voltage, it is applied to loads where the required torque decreases substantially as the speed is reduced, such as a small squirrel cage motor driving fence. Variable voltage can be achieved by using saturable reactors, variacs or tap changing transformers. Now, we will discuss the methods where speed control is achieved from the rotor side. So first one, speed control by changing rotor circuit resistance. As we have discussed, the wound rotor motors are typically started with additional rotor resistance connected in the secondary circuit, and these external resistance, they are gradually bypassed as the motor accelerates. So, initially external resistance is inserted in the circuit, and gradually we will cut off this resistance. So, if the resistances are properly selected and designed for continuous use, they can be used for both starting of the motor as well as speed control of this motor. This method is exclusive to wound rotor type motor, as there is no provision of insertion of resistance in cage type motor, already we have discussed. The smoothness of this speed control is dependent on the number of available resistances, the steps for which provision of changing is available. Accordingly, the speed steps can be obtained. This method allows speed control only below the base speed. The range of speed control varies with the load and is not constant. Speed variation is limited to a range between 50% and 100% of the base speed. Now, the next method for speed control through secondary foreign voltage control. In this method, the speed of an induction motor is regulated by injecting a slip frequency voltage into secondary circuit. When the injected voltage is in phase with the induced EMF in the secondary circuit, the rotor circuit, it effectively reduces the resistance in that circuit, leading to a decrease in the slip and increase in the speed. So, this allows for achieving supersynchronous speed also, and conversely, if the injected voltage is out of phase with the induced EMF, it acts as if increasing the resistance in the secondary circuit, which results in higher slip and hence the reduced speed. So, this technique offers a broad range of speed control by incorporating a frequency converting equipment in the rotor circuit. While this method addresses the issue of lower efficiency and poor speed regulation, it is more expensive due to the need of the one or more auxiliary machines to inject the slip frequency EMF. As a result, this is typically used in very large motors such as those found in steel mills. So far, we have discussed some methods of speed control from stator side and from rotor side. Now, we will discuss speed control by cascaded operation. In this method, we are having two motors. The first motor, motor A, second motor, motor B. Both the motors are wound for different number of poles. Suppose the number of poles of motor A is PA and that of second motor is PB. Now, we are having three options. If we connect supply to the motor A alone, only to the motor A, the combined shaft will run to the speed based on Ns is equal to 120 F upon Pa. This is the first option. In second case, we are not feeding any power to motor A. Simply we are feeding power to motor B. And what will be the synchronous speed of that motor? Ns will be equal to 120 F upon Pb. So, accordingly, we are getting two different speeds. Just see, rotor of both the motors, it is common. If we are supplying power to only A, the final combination, the shaft will rotate at a speed corresponding to Pa number of poles. If we are feeding the power to only B motor, then the shaft speed will be according to 120 F upon Pb. Now, in third case, here the output of the slip ring of motor A, it is fed to that of stator of B. So, what we are doing? Supply input power to motor A. Suppose EMF induced is in the stator winding is E1. At that moment, what will be the voltage available at the slip rings? We know that SE2 is the voltage induced in the motor. But since 1:1 turn ratio is there between stator and rotor of motor A, so EMF induced is SE1. So, this time what is input voltage of B? It is SE1. Now, this final speed of the shaft will be equal to N is equal to 120 F upon PA, P1 plus P2 or PA plus PB. And if we interchange any two of these leads of the second motor, supply to the stator of second motor, then it is known as differential cascading, and in that case speed will be N is equal to 120 F upon P1 minus P2. And here again care has to be taken. P1 minus P2 will become 0 if number of poles of both the motors are same. So, it is also the third condition, same number of poles should not be there. We have seen the speed control of induction motor, which can be achieved from stator side by changing the number of poles to the stator winding, by changing the frequency of applied voltage, by changing stator voltage, and from rotor side changing rotor circuit resistance, changing foreign voltage control, and finally we have seen the cascaded operation also. In the next class, we will study the principle of operation of synchronous motor. But before that, before completing today's lecture, I must suggest that speed control, this topic should be studied with controlling your speed of study, because I have seen many students, when the question is asked, describe the speed control of induction motor, and they used to start answering starting of induction motor, and they write it pretty well. But as a teacher, I cannot award them marks, because question was about to speed control and they are describing starting of induction motor. So, just maintain your speed. All the best. Thank you.